Chapter 2 continued, Section 2.6, Combinations of Functions and Composite Functions. These are actually two different quantities. Let's take a look at the objectives. We're going to combine functions using what's called the algebra of functions. That means we're going to be adding them, subtracting them, multiplying them, and dividing them. That's called the algebra of functions. So we'll have two functions and we'll be combining them. We'll also be finding the domain of that combination. Then we'll do something different, which is called composite functions. This is combining them in a different way other than add, subtract, multiply, and divide. We'll also be finding the domains for those composite functions. And then we're going to take two functions, and instead of combining them, we're going to do the reverse. We're going to write a single function and split it apart as a composition of two functions. So let's get started on that. Finding a function's domain. If a function f does not model data or verbal conditions, why that says this is because verbal conditions can often specify that a quantity is only good for this value to another value, and that automatically defines the domain, even though the function may be defined beyond that. And if it models data often, say with time, then time can't be negative, so there's an implication of domain right there. So we're talking in a generic sense. The domain is the largest set of real numbers for which the function is defined. And when are functions not defined? Well, in a basic way, we have to exclude numbers that cause division by zero. So that occurs when you have rational functions, quotients of things, and denominators. And when you take even roots, like square root, fourth root, sixth root of a negative number, that results in a non-real number. So that has to be excluded. Let's take a look at an example. Example 1. Find the domain of the function g of x equals 5x divided by x squared minus 49. Okay, if you want domain, you look at the function and say, are there any square roots, fourth roots, sixth roots? Well, no. Is there a fraction where the denominator could be 0? Yes, we have a denominator here. So we immediately target how the function can be not defined is by division by 0. So we'll take the denominator, we'll set it equal to 0, and we'll solve for x. So you have to exclude these values. These are the two values for which the function is not defined. However, domain is written to give the values of x for which it is defined. And here's a way to do this. You draw a number line. You have to exclude negative 7 and 7. So I'm going to put an open circle above those two numbers indicating that we cannot use those. But we can use anything to the left. That means the interval negative infinity to negative 7. The open parenthesis here indicates not included. We can also have everything between negative 7 and plus 7. That's this open interval right here, not including the endpoint, so we're using parentheses here. And then we can also use anything that's greater than 7, which is this interval right here, not including 7 to the right forever. The U represent union, which means put all three of those pieces together. This interval included with this interval, included with that interval, that's the union. And all of this are the allowable values of x that you're allowed to use that would make the original function properly defined. Let's move on to the algebra of functions. Adding, subtracting, multiplying, and dividing functions. That's called the algebra of functions. Okay. There's a lot of notation that comes with it, but it's very, very simple. To add two functions together simply means, in an alternate notation, f plus g evaluated at the value x. That just means take f of x and add it to the function g of x. In a similar way, the difference is defined, and in a very similar way, the product is defined. So f times g evaluated at x simply means take the product of the two individual functions. And the quotient, written in this cumbersome way just means to take the function f divided by the function g. So let's do some specific examples. Let f be the linear function x minus 5 and g be the quadratic function x squared minus 1. Let's add the two functions together. So literally take this function f of x, which is x minus 5, add it to the other function called g of x, and where we have like terms, you can add like terms to get your result. Okay, what is the domain of that new function that's been created by addition? Okay, well, f of x has no restriction. It's polynomial. It's defined for all values of x. This one has no restrictions. It's defined for all values of x. Therefore, the new function created also has no restrictions. No restriction mean that you can use the entire x-axis and all numbers on the x-axis. So that means left forever and right forever, all numbers on the x-axis. In other words, this says all real numbers are allowed to be used in our new function created by addition. We'll do more specific examples when we work at the problems. Let's take a look at the composition of functions. This is a much different idea. If you look very carefully here, the composition, this is not a dot for multiplication, this is an open circle. This means composition. So the word composition means to put things together. This is the notation f compose g. Okay, that notation doesn't help the understanding very much, but it's equivalent to this notation here. F compose g simply means f of g of x. It means to put the g of x function, the whole thing, inside the f function. So it's a replacement of the variable not by a number but by an entire function. The domain can get a little tricky, and we have to look at this case by case, and I think it's best to move on to some examples to show and then give more detail when we work the problem. Example 3. F is the linear function 5x plus 6. G is the quadratic function shown. Find f compose g. Say, first thing I would do is take the ambiguous notation and write it with the notation that provides more understanding. F of g of x means go to the function f. Everywhere you see an x, you're going to replace that x by the entire g function. So since g of x is 2x squared minus x minus 1, all of that gets substituted right in there for x. There it is. Instead of 5x plus 6, it's 5 times g of x plus 6. And then you can distribute the 5 and clean it up and add like terms where you need to. And it is possible to compose functions in the opposite way and do g compose f. And that will be done in the problem section. Let's take a look at the domain of these composite functions. This can get a little tricky and a little wordy. So again, examples are more powerful than descriptions. The following values must be excluded from the inputs of x. Let's see. If x is not in the domain of g, it must not be in the domain of f compose g. So first you got to go to the g function because you're putting g inside f. And if there's any domain restrictions on g, it is immediately out and you record that on paper. Now you make the composition, f compose g. Then you look at the domain of that new function, the composition of f and g, and you see if there's any values that have to again be excluded. Then you put both domains together and quote the domain of the new composition. This is paraphrasing what it says here that you're reading. Let's look at an example. We have a rational function for f and a rational function for g. We're going to compose them in the following way. F compose g. Okay, so first thing is write it in better notation. F compose g of x means f of g of x. Okay, so literally f of g of x means go to the f function, replace x by g of x. So instead of 4 divided by x plus 2, it's 4 divided by the g of x function plus 2. Well, g of x is 1 over x. So replace g of x with 1 over x, and this is now the composition. And we can clean that up a little bit by getting rid of the complex fraction. If you multiply the top by x, 4x, multiply the entire bottom by x times 1 over x is 1, and x times 2 is 2x. And now this is cleaned up. Okay, now we have to look at the domain. First thing, we took f of g of x. So you have to look at the g function first, which is here. Are there any restrictions? Yes. We have a fraction here where there's a denominator, and the denominator can be 0, x can't be 0. So right away you note that one on paper, x can't be 0. Now you form the composition as we have done here. Notice that this new function is still defined where x is equal to 0, but it's already been restricted and thrown out of the domain, and you have to keep that in mind. Now, were there any additional values here for which this is not defined? And the answer is yes, because the denominator can be 0 when x is negative 1/2. So this is a new restriction on the composition. So our new domain, whatever it is, cannot include 0, and it cannot include negative 1/2. So if we move to the next slide, we'll see that this is the description that's being discussed. So we know for the function g of x, x can't be 0. We know for the composition, x can't be negative 1/2. Now, how do you say that in interval notation? Again, I suggest you draw a number line, you locate negative 1/2, and you locate 0. You cannot include negative 1/2, and you cannot include 0. But anything to the left of negative 1/2 is acceptable. Anything in between negative 1/2 and 0 is acceptable, and anything to the right of 0 is acceptable. So there are 1, 2, 3 intervals that must be quoted. That's why there's 3 here. Everything to the left of negative 1/2, open parenthesis, not including negative 1/2, together with everything between negative 1/2 and 0, and finally together with everything to the right of 0. And these are the allowable values of x that can be used. One more example. Here we have a function called h of x. And we wish to decompose that function into 2 other functions. In other words, we want to rewrite this function as 2 functions so that the composition of those 2 functions would yield this function here. This is an idea that's important in calculus. So when I look at the h of x function, I see 2 functions. I see the function that's doing the square rooting, and then I see the function that's being square rooted. Those are the 2 individual pieces. So one function is the square root function. The other function is the one being square rooted. Now you have to figure out whether it's f compose g or is it g compose f. So let's see. If you put all of this, which is g of x, inside there, you get the original. Putting g of x inside f means f compose g. It means f of g of x. And if you try it the other way, if you try g of f of x, sometimes in math you just have to try it and see if it works out. That's putting the f of x function inside the g function. So that's g of root x. Root x is your f function. And that means go to the g function and replace the variable by root x. So that would be root x squared plus 5. And that is certainly not equal to the original function h of x. So this is the wrong composition, and this is the correct composition.